So now that you have all taken the time to work out these 18 problems as best you can, let's take a look at how these could come together. So number one, pretty simple. We have a hydrogen here with one dot. And notice that when I do Lewis structures for the other hydrogen, I'm just going to take the S and put it over here. Conventionally, we put the S's over on this side, but for the sake of bonding, let's do it over on this side. So we see that obviously those two are going to share, so this is a full octet here, and so if we're going to make it nice and pretty, we go and do that. So there's a single shared pair of electrons, meaning that this electron is going to spend time over here, and this electron is going to spend time over here, so both are satisfied with their full octet. Now, we take a look at number two. Number two is one that we take a look at, and we see oxygen, two S's, 1, 2, 3, 4 P's. We have a hydrogen here with one dot and one over here. Obviously, we're going to see that these two are going to share, and these two are going to share. Now, I want to introduce another concept here. We're going to use this to figure out some angles and shapes later on. Notice that around this oxygen, if I was going to clean it up, I have two shared pairs of electrons represented by these lines, that's these loops that we made, and two unshared pairs. Okay? Now what this means is that the electrons on this side are not bound to anything, and they're going to be free. They are going to have a greater repelling power, and that's what Vesper is really all about. This is going to be important in determining our shapes. It's also going to be important in determining something called polarity. So here we see that we have electron heavy on one side, even though overall the entire compound is neutral, we find that it is electron heavy on this side and this side, so we would refer to this as a slightly negative end or pole, and this would be a slightly negative pole. And this would be, since the electrons are found more heavily on that side, that would make this more slightly positive and this more slightly positive. It is a polar molecule, just like a magnet, where we have a negative and a positive end of it, and what that ends up translating to is, if we introduce another water, within that, what's going to happen is the slightly negative side of this is going to stick to this. It's going to be attracted to it. Electronegativity wise, they're going to be attracted to one another. So they're not bonded together. I want to be clear on that. It's not a chemical bond, but they are going to stick together. And so we find that water is actually a very sticky molecule because it is highly polar. So we have the term polar, and we have unshared pairs. Now we take a look at number three. We have nitrogen, 1, 2, 3, 4, 5, and we have 3 hydrogens. It's pretty easy to see that we're going to have one hydrogen here, one hydrogen here, and one hydrogen here. Pretty easy to see because the hydrogen only has one dot to work with, so we see that we have one lone pair of electrons that is unshared, and we have 3 shared pairs of electrons. It is still a polar molecule, not quite as polar as water would be. We have a slightly negative end on this side, and we have 3 slightly positive ends on this side. So introducing those concepts and working them and seeing how they work. Okay, so we have shared pairs, we have unshared pairs. We have another example, hydrochloric acid. We have just simply one dot, and we have chlorine 1, 2, 3, 4, 5, 6, 7. So obviously we're going to see that this is going to go and share right there. So hydrochloric acid would also be considered polar because look at all these electrons on this side, and there's none free up on this side. Okay, so the concept of polarity is actually quite simple. Now, we have another concept here coming up with number 5. We have nitrogen gas. So there's 2 nitrogens, 1, 2, 3 P's. Let's put another nitrogen over here. Let's put its S's on this side just for the sake of ease. And so up to this point, we've always been sharing just one time between elements. But now we see that actually we could share a second time and a third time. We have to do that to satisfy the octet rule. So the first time something is going to be shared, that's a little Greek symbol called the sigma. So the first time something is sharing, it's actually sharing at the S sublevel area. So the sigma is this Greek letter right here, and that means that the second time, and in this case the third time, it's bonding at the P sublevels. These are what we refer to as the pi bonds. Okay? Now we think math-wise we have the number 3.14 and so on, but this is actually pi because it's referring to the Greek letter P, because it's bonding at the P sublevels. Now I don't care which one, actually when we see and clean it all up, we see that nitrogen is going to bond 3 times like this, so clean up my loops and just make lines, I don't really care which one of those is the sigma bond in there. The concept is the first time that something has been bonding, all of these other ones that we've been doing, those have all been sigma bonds. But whenever we introduce a double bond or a triple bond, then what that means is that the elements just get tighter to one another, and those are pi bonds because of the p overlap. Now, another term that I showed you that came up with the example video that, for number 6, it was carbon dioxide. Okay, so carbon. I know that we always start carbon this way, okay? And oxygen goes like this, and I'll put the other oxygen over here, the S is over here. Okay, now, we always start with carbon this way. However, I introduced, just in a little example video, that carbon loves to hybridize. Hybridization is shuffling of an electron from one normal sublevel into another one to accommodate, to make space. And the reason that would happen is we would find that if I were to consider that these S's are locked up, I would see, okay, I'm going to combine one here, and maybe I combine this one over here. But you see that oxygen here and here still need some electrons. Carbon has 2, 4, 6 electrons, but we still are missing 2. So what would happen if I were to take one of these S's and create room? And so what would happen is I would form another bond with oxygen, and this one would form a bond as well. Now, to clean it all up, what did I end up with? I ended up with a pi bond on each oxygen. And the reason that happened is because I shuffled one of the S electrons out to the P. So I hybridized that. Now, if we want to get really technical with it, we had 2 S's and 2 P's, so we'd have a special type of hybridization. Okay, so we call them SP hybridization, SP2 hybridization, or SP3 hybridization, and so on. So it's just, the concept is that these carbons will always hybridize to accommodate for other room. Now, around here we would also remember that I have 2 sigma bonds, and these top ones would be considered pi bonds. Okay, so around carbon, it's actually, there's no other electrons available. And remember what pi bonds do, they just bring it tighter. So I would consider this just being 2 electrons on one shared on this side, one shared on this side. The pi bonds just make it stronger. Another point that brings up is polarity. Notice that on this molecule, I see that these electrons, these free electrons over here, the unshared pair of electrons is here, but it's the same equal amount on this side. This is a non-polar molecule because it's exactly the same on both sides. It's not electron heavy at any point. Okay, so we take a look at how that would work with carbon dioxide. Now let's take a look at sulfur dichloride. Okay, sulfur has the same electron configuration as oxygen. Chlorine, 1, 2, 3, 4, 5, 6, 7, and we'll put the other chlorine here, 1, 2, 1, 2, 3, 4, 5. Okay, so we've got 7 total on each side. Pretty easy to see that this guy goes like this and this. Now notice that when I clean it up, sulfur has the exact same behaviors and characteristics as water would have, because I see around this sulfur I've got 2 unshared pairs of electrons, and so it's a good time to start to introduce another concept. And this concept is, how do we interpret this? I see 2 shared pairs of electrons around the core, and I see 2 unshared pairs of electrons. Well, this influences the shape. So if we're taking a look at shapes, there are some rules that govern what shapes things might have. Okay? These shapes we can interpret based on what we see for different types of combinations. So if I see we have an example where we have 2 shared and 0 unshared, we would say that that shape is linear in shape, and so at an angle of 180. So just visually what we'd see is around this core is 0 unshared pairs, and we'd see electrons on this side. Now a good example of that is actually carbon dioxide. The reason I say that is because you might say at first, because these pi bonds, you might say, wait a minute, there's four shared pairs. But remember with this, all those pi bonds do is actually make that a little bit tighter in. It doesn't influence the shape at all, it doesn't do anything. So we really, for the sake of figuring out angles and all that, we only really count those sigma bonds. So around this we would see two shared pairs. Around the core we'd see 0 unshared pairs. Okay, don't count the outside, the perimeter ones, because we're looking at angles. To have an angle, you have to have 3 points. Okay, so there's my angle. You don't consider out here what's going on. You just look at what's going on there. So if I have an example of 2 shared and 0 unshared, we call that shape linear, and the angle itself is 180. This is something you're going to have to memorize. If I take a look at the next scenario, I would see an example of 3 shared and 0 unshared. Now at first you might say, well, how can that be? Because if I count up shared pairs, that's only 6. But what if we had an example of BCl3? Now boron itself only has 3 electrons to work with. So what we would do is we would hybridize this. So boron would then have 1 electron, and obviously we'd have a chlorine with all of its unshared pairs sitting around here. And here's my third one. Okay, now I know I drew it out that way, but technically what's going to happen, because these are going to be repelling, is we have an angle of 120, so it looks more like this. Okay, so just kind of make sure we're thinking in terms of geometry, and we're looking at how this might work. We see other examples like 2 and 2, that would be our water example. We refer to that molecule as bent triatomic in shape. The angle there would be 105. We have other examples of 3 and 1. Okay, we'll see like ammonia and things like that. We have 3 shared, 1 unshared. It's pyramidal. The angle is 107. There are times when we have something that is very stable. It's 4 shared pairs, 0 unshared pairs. We refer to that as tetrahedral, tetra meaning 4, and the angle of all those is 109.5. It's not going to be this straight up, just kind of looking like this, where it's a 90-degree angle. We got to think 3-dimensionally. So the angle is actually 109.5. And there are some weird scenarios. You'll see one coming up where we have 5 shared, 0 unshared. We refer to that as trigonal bipyramidal, and the angle is technically less than 109.5. There's a lot of shifting and vibrating going on with that, so it's not like it's going to be the same every single time. Okay, we've been looking at some of those things in terms of shapes. Okay, so we've hit terms like shared pairs, unshared pairs, hybridization, polar, nonpolar, sigma bonds, pi bonds, and then we have our shapes and angles. But the question is, why does this happen? Okay, when we take a look at the different shapes that emerge and the different angles that emerge, it all has to do with what the Vesper theory actually stands for, the valence shell electron pair repulsion theory. And it goes like this. It says, and I always use the example of just kind of an elementary playground. We have this big old playground, we have this big old area to work with, and we have, let's say we have 2 big 5th graders, okay? They own the entire playground, okay? Now if they split it up, they kind of live in peace. They go inside, now all of a sudden come out all the kindergartners, and they're going to be bouncing all over the place. They take up the whole space, okay? So the entire area is going to be influenced. Now, what happens if one of those 5th graders comes out? He represents maybe the unshared pair. What's going to happen? All those kindergartners that were all spread out here now are all of a sudden going to be confined to maybe a smaller area, because this one lone unshared pair of electrons, represented by the 5th grader, would take up or repel those elementary kids, those kindergartners, into a smaller area. So if I have an example of, say, carbon tetrachloride, like this, those chlorines are going to be spread out as much as possible, and that angle between all of those is 109.5. But what happens if I do this? If I have some unknown element, okay, let's say it's nitrogen or something like that, and so we only have 3 chlorines. If I have an unshared pair, what's going to happen is he's going to force these chlorines closer to one another. Why? Because they're shared. This unshared pair of electrons has a higher repelling force. Now what happens if we switch it, and now all of a sudden it's not just nitrogen, but maybe it's oxygen? where we have two unshared pairs. Well, these guys are going to split up. Imagine two fifth graders with all little kindergartners. What's going to happen is these fifth graders are going to split up the area equally amongst themselves and force those little kindergartners into an even smaller space. And so what happens is these unshared pairs have a much larger repelling force against each other. They're going to spread out, forcing these guys even closer together. So there's a hierarchy here. It goes like this. Shared pairs have a lesser repelling force than shared to unshared, which have a lesser repelling force than two unshared pairs. Now, this is kind of a weird concept when we take a look at that. It's kind of weird at first when you try to decode it, but again, think of the examples. If we have something where we have carbon and your chlorines, these are all shared pairs, so they're going to repel each other, and they're going to repel each other, they're going to push out and spread out as much as possible. However, what's going to happen is, if I introduce, say for example, an unshared pair of electrons here, this guy is going to push against these even more than these guys are going to repel. Okay, so this is an example of shared pairs versus unshared pairs. He influences the shape, and that's why we see the difference between 120 and 107. And then we have the example, say, of water, where we have two unshared pairs. Okay, so these unshared pairs are going to repel each other even more, even stronger, which forces these two even closer to one another. And so we see the example of two shared and two unshared. Yep, we see it's even smaller angle. Okay, so think about that in terms of your examples and what we would see for those.